In this video, we would like to present our work on attention-guided masked autoencoders for learning image representations, which is presented at WACV 2025. Masked autoencoders are especially popular for weight initialization of vision transformers when fine-tuning a model, but we find their off-the-shelf feature representations like high-level semantic understanding, which limits their performance for settings such as linear evaluations. We propose to address this shortcoming by formulating a simple yet effective way of inducing high-level semantic understanding into masked autoencoders through attention maps, which distinguish the foreground semantic object from the rest of the image. Recent progress in unsupervised object discovery has enabled robust extraction of attention masks that capture the semantically most relevant foreground object. We find that with a simple but effective modification, we can induce semantic relevance into the representations of the masked autoencoder. For this, we manipulate the reconstruction loss of the masked autoencoder to put additional emphasis on foreground objects through patch-level reconstruction loss reweighting. Following the standard masked autoencoder protocol, we first mask 75% of the image patches and pass them through the encoder-decoder architecture to reconstruct the masked patches and calculate the reconstruction loss. At the same time, we pass the full image for our unsupervised object discovery network to obtain a raw attention mask. We then pass this attention mask for our scaling function, where it's normalized, sharpened with a temperature parameter tau, and inserted into the exponential function. Finally, we multiply the scaled attention mask with the loss of the reconstructed patches, effectively performing a semantic reweighting of the loss. Let's have a look at our scaling function in more detail. Through the exponential function, background patches with original values of 0 are now scaled to 1. We found this step to be important, since all background reconstruction learning signal would be otherwise cancelled out. Furthermore, our sharpening parameter increases the weight of the patches with the highest values, putting additional emphasis on the foreground. We train a VIT large for 1600 epochs, following the standard masked autoencoder setting. After pre-training, we freeze the encoder VIT and perform 2 sets of tasks. We add a simple linear layer for image level classification and see consistent performance gains across a wide range of datasets. Furthermore, we perform semantic segmentation and other tasks from the taskonomy dataset and see consistent improvements. In our paper, we present an extensive selection of further experiments. As part of our evaluations, we experiment with different sources for attention maps, but find token cut maps remain most effective for our approach. Further, we experiment with different ways of guiding the masked autoencoder, such as inverting the attention map or masking the input with it. Across all variations, our guidance performs the best. Thank you for watching our video. If you would like to learn more about our work, we invite you to visit our project page or get in touch with us.